Hi, so good morning. Welcome again to this another series lecture. We are already in the fifth of the sixth review for our in preparation for our written examination. So again, as a reminder, you have to study all of these problems here because all of the problems are basically the same of all the problems that will come out in your written examination, in your written assessment. But we have to tweak some of the values, some of the words there in order for to really check if you really understood what the theory or the fundamentals of electrical theory. So before we proceed, I would like to remind you again, if this is your first time watching this lecture, you may study along with me. But if this is the second time, before we start answering each question, pause for a while and then try to answer on your own. And then later on, compare some answers and then check if you've really understood the problem. Okay, if you have some problems and then some questions, you may comment in the section below. Okay, so let's start answering this question here. Number 41. So if a 6 volts and a 19 volts battery source are connected series aiding, the total voltage is. So in the previous lecture, we only discuss loads connected in series. Loads connected in series. Resistors connected in series. But in reality, in practice, there are also some cases that voltage source or the supply voltage are connected either in series or connected in parallel. Okay? In most of the practice, happens all the time that batteries are connected in series. And mostly it is connected in aiding. Okay? And then another sets of batteries are connected in parallel to increase the rating. But in this particular case here, what do you mean by aiding? What do you mean by opposing? Okay, the aiding and opposing is basically you have a resistor or you have a power supply or you have a battery. You have a battery. Take note that the battery have a polarity. A battery have a polarity, a positive and a negative. Okay, and then you have here another battery which is positive and negative. Okay, so what do you mean by aiding? Aiding happens if you are going to connect this one. If you have a wire here, let's have the color blue. If you're going to connect this one, the output is the negative. This is the first output. Okay, and then you're going to connect the positive here in the negative here, and then this output of the positive will be here. And then this final output here is the positive, and then this final output here will be the negative. Okay, so in this way, this is how we connect two voltages in aiding. Aiding, it means to say that it helps each other. Okay, what will happen if we incorrectly or we connect this one? Let's say, for example, instead the positive here, it was connected in the positive, not the negative. So that is in that particular case here. Let me draw this one. So this one, this is for uh, aiding. And then the other one, what will happen if we use the block? Okay, the positive, negative, positive, negative. So the other one, the other configuration, the aiding, the opposing is the negative is connected here. Oh, let's use the blue. Okay, the negative is connected here. So this will be okay, and then the positive, instead of connecting it to the negative, it was connected to the positive, and then the negative here connected here. So in this case here, this is opposing. This configuration is opposing. Okay, the output voltage of the two will be different. Okay, so in this particular case here, number 41, if 6 volts and 19 volts are connected in series in aiding, so it means to say you can just add the two values. So the two values, 6 plus, so 6 plus 19 volts, so 6 plus 19 volts, that is equal to 25 volts. So that is the 25 volts here. Okay, so that is for series batteries. Next, number 42. 5 resistors are connected in series and there is a current 3 amperes into the first resistor. So the amount of current in the second resistor is. So this is very confusing. This is very tricky question. Okay, let's try to draw this one to really appreciate this. Five resistors, but the problem did not state what are the values of these resistors here. Okay, and then it does not also state what is the value of the voltage source. Okay, so we really have to understand the fundamental theory here. So you have a voltage source here, and then you have a resistor. In this problem, it was stated that there were five resistors connected in series. Okay, and then the problem also stated that the first resistor, the current in the first resistor is equal to 3 amperes. So the current flowing in the first resistor is 3 amperes. Now, the question is, what is the current in the second resistor? Okay, so again, let's go back to the basic principles of current in a series circuits. In a series circuit, the currents are the same. I source is equal to I1 is equal to I2 is equal to I3 is equal to I4 is equal to I5. So, in this particular case here, the answer will still be 3 amperes. Okay? Take note of that. Number 43. The total resistance of 1K resistors connected in series is very simple. Again, in our previous discussion, the resistance to solve for the total resistance in series, that is equal to the R total is equal to R1 plus R2 plus in this particular case here, R8. Okay, so what are you going to do? You just have to add the 8 resistors, 1K each, so that is equal to R total is equal to 1K times 8 because you have 8 resistors. So basically what you have is 8,000 ohms. Okay, very simple. Next, a series circuit has a 12-volt source and a total resistance of 240 ohms. The current through each resistor, so basically, connected in series. If we can compute for the R total in this particular case here, we can compute the resistance of each the current of each resistor. So basically, what we want to do here is we will just have to divide this one here. So again, the formula of our VIR, and then solving for our I. So I is equal to V over R. So the voltage here is 12 volts divided by 240 ohms. That is equal to 12 divided by 240. 0.05 ampere. So this is the answer. But since the value is less than 1 ampere, we can solve this one into milliamperes. Okay, again, and again, the conversion factor will be 1 ampere is equal to 1,000 milliampere. But in this particular case here, since what we want to do here, the final unit that we want to have is milliamperes. So that is why in this conversion factor, we have to rotate this one. And then make sure that the final unit that you want to have will be put in the numerator. So in this particular case here, we can multiply this one by the conversion factor, 1,000 milliampere, because we want the milliampere as as our final unit. So this is 1 ampere. So it will cancel out this ampere. Okay, and then we just have to multiply that 0.05 to 1,000. So that is equal to 50 milliampere. Okay, so as simple as that. Next, number 45. Again, let me pause you for a while. If this is the second time that you've already watched this video, pause for a while, try to solve the problem on your own in a couple of seconds, and let's compare answers later on. Okay? So, number 45. To measure the current out of the second resistor in a circuit consisting of 4 resistors, an ammeter can be placed. Oh, this is a very tricky question. To measure the current out of the second resistor in a circuit consisting of 4 resistors, an ammeter can be placed. So take note. Okay. So in this particular problem here, so you have a voltage source and then you have 4 resistors. Okay. Take note again, guys, that if you are going to connect a voltmeter, voltmeter should be connected in parallel in parallel to the loads, okay, in parallel to the loads that you are going to measure. So what it means is that if you're going to connect a voltmeter here, if this is a voltmeter or multitester, you are going to measure this one by tapping in the terminals of these loads here. Okay? So again, take note if you're going to connect a voltmeter, you have to connect this one in parallel with the load that you are going to measure. However, if you're going to connect an ammeter should be connected in series. Okay? It should be connected in series to the load that you are going to measure. For example, in this particular case here, you want to measure the current flowing through this line here, through this load here. Let's say this load here. You want to measure that current. In order for you to connect an ammeter, okay, to measure the current for this particular load here, you are going to connect this one in series. So basically, you're going to remove this one. Okay, remove a portion, and then you are going to connect the ammeter here. You're going to connect the ammeter in series with the load that you are trying to measure. Okay? So, in this particular problem here, to measure the current out of the second resistor, in this resistor here, we want to measure the current in this resistor there, consisting of 4 resistors. The ammeter can be placed. So, basically, if the assumption here is the resistors are connected in series, so it means to say that either you put the ammeter here, you put the ammeter here, you put the ammeter here, you put the ammeter, you put the ammeter here. You can put the ammeter in anywhere of that circuit. The value of the current will be the same because in the theories that we've discussed in the currents in a series circuit, all the currents are all the same. Okay, so that is why you can put the ammeter, assuming that this circuit is connected in series at any point in this circuit. Okay, so that's good. Now, let's proceed with a number 46 here. If 14 volts and 17 volts battery are series opposing, the total voltage is. So on the previous lecture, we discussed if it is aiding, you have to add the resistor. You have to add the voltage. Okay, but in this particular case here, since they are opposing, the voltage are opposing, so that should have a 14 volts minus the 7 volts. It should be 7 volts. But also, there are also some cases that the polarity, you have to take note on the polarity of or the positioning of the battery that you are going to have. Okay, although it was not stated clearly in this problem, the orientation of the battery, but let's assume that the connection will be like this. So positive, negative. So this is the 14 volts. And then this is the positive, this is the negative, this is the 7 volts. And then you want to measure here, around here. Okay, if you are going to connect the voltmeter here, okay, and this is the positive, this is the negative, you will are going to have the positive 7 volts. Why? Because let's assume, the other way to assume this one here, to understand the concept of the series and series batteries opposing and aiding, is try to consider this one as a source of tsunami or a source of wave, something like that. If this is 14 volts, okay, if this is the 14 volts, and then the wave of this particular voltage here is through like that, okay, that's the wave. Okay, that's the wave of the 14 volts. Okay, a little bigger wave. Okay, however, on the 7 volts, okay, a shorter wave. Okay, so that is why this is the opposition. This is the opposing voltage. So that is why after the 7 volts, okay, the wave after the 7 volts will be a little bit smaller. Okay, this 14 volts here will have a little bit smaller because of the reduction of 7 volts there. Okay, so that is why the output voltage here is only 7 volts. However, if I'm going to arrange this one into aiding, okay, so that is plus minus, and then you have here plus minus, and then you're going to measure here the voltage here, plus minus voltage here, and then this is 14 volts, and then this one here is 7 volts, and then this is aiding. Okay, take note, the positive is the direction of, indicates the direction of your wave. So in this particular case here, the direction of your wave here is through this line here. And then the direction of the wave for the 14 volts is through there. So in this particular case here, this is opposing. Okay, and if this is aiding, okay, so we're going to illustrate this one using the wave again. Okay, the wave for the 14 volts is something like that, and then the wave of the 7 volts, since the direction of this 47 volts is in that direction, so basically you can also add that one with this wave here. So that is why the total wave will be a little much bigger. So that is why the answer for this case here should be 14 plus 7, that is equal to 21 volts. So this is for aiding, okay, and then 7 volts for opposing. Okay, so just take note of that. Okay, it looks like a monster, a monster clause or something like that. Okay, so that's the art of digital blackboard, digital whiteboard. Okay, now let's proceed with number 47 here. So a series circuit consists of three resistors. Two resistors are 1.5K each, and the total resistance is 15K. The value of the third resistor, this is very simple. So to illustrate this one, you have three resistors, and we have here as our R total. And then based on the problem here, two resistors are 1,500 each. So 1.5K, this is 1.5K, 1,500. And then this one here is unknown, but the total resistance is 15K, okay, or 15,000. So to solve for this R here, R3, okay, let's go back to the formula on solving the total resistance in a series circuit. So that is equal to the R total, okay, the R total is equal to R1 plus R2 plus R3. Okay, the R total is already given, that is 15K, is equal to the R1 is 1.5K, this one is 1.5K, and then this one is unknown. The R3 is unknown. Simplifying, oops, R3. So simplifying, this is 15K equals 3K plus R3. Transpose this one to the other side. So we have 15K minus 3K is equal to R3. So 15 minus 3, that is equal to 12K, is equal to R3. So the value of your third resistor is 12,000 ohms or 12 kilo ohms. Okay, this is the answer for this particular problem. Next, number 48. So this will be the last three. We are on the last three for this particular video. Okay. A current into junction flows along two paths. One current is 4 amperes and the other is 3 amperes. The total current out of the junction is, so basically what the problem is talking about here is you have a junction. Okay? A junction, basically an electrical junction is a junction like that. Okay, something like that. So you have some nodes here, maybe you have some resistors there, some resistors here, you have some resistors. But basically, this one here is a node or a junction. Okay, so according to this problem here, the one current is, so basically we cannot assume that this is a resistance, but basically the junction is looks like this. Okay, so the current into along two paths. Okay, one current is 4 amperes. Okay, this is 4 amperes. And the other is 3 amperes. So therefore, the total is, in a node, you just have to add the current here. 4 amperes plus 3 amperes, of course, this is 7 amperes. So this one is very common in a parallel connection. Okay, maybe we will have some problems related to this kind of problem here in the next lecture. Okay, so number 49. When additional resistor is connected across an existing parallel circuit, the total resistance, the answer will be decreases. We have to take note that on the previous lecture, if we're going to add, for example, the previous discussions that we had, if you have an existing series resistors, and then you are going to add another resistor, okay, the total resistance increases. Why? Because this is additive. Additive. You have to add all the values of the resistors there. So therefore, the total resistance increases. However, when we are talking about the parallel here, the more number the resistors you connect in parallel, the lower the value. The lower the value. What do you mean by that? Okay, so let's assume a value here. So let's have okay, let's have 10 ohms here. And then we have here 10 ohms. Okay, so that is two resistors. So if you're going to solve for the total resistance here, okay, the R total here, we are going to have the R total is equal to R1, R2 divided by R1 plus R2. That's the formula to compute the total resistance in a parallel circuit. So now let's substitute. That is 10 multiplied by 10 divided by 10 plus 10. So that is 100 divided by 20. So 100 divided by 20, that is equal to 5 ohms. So the total resistance in this particular case here is 5 ohms. So take note that the original resistors here are 10 ohms. Then you connect another 10 ohms, that is equal to 5 ohms. Only 5 ohms. Now, what happens if you connect another, okay, another 5 ohms, another 10 ohms. Okay, so the equivalent resistance here is already, okay, so let's try to solve it in a manual way. Okay, okay, so let's have this one as 10 ohms again, 10 ohms and then 10 ohms. So to solve for the total resistance in a parallel circuit, given that all of the values here are the same, okay, let's do it in the longer way. So the R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So that's the formula there. But in this particular case here, what we can do is we can parallel this one first. Okay, we can solve this one as two resistors, and then the resulting value there, we're going to parallel it again to the 10 ohms. So basically, in the previous one that we have here, if we're going to parallel two 10 ohms, the resulting value is 5 ohms. So basically, if we're going to solve this one first, as this one as a 10 ohms parallel with 10 ohms, so we will have 10 ohms, and then the new, which is the connection, the parallel connection of these two here, will be 5 ohms. This is the 5 ohms here is the equivalent of the parallel between the two 10 ohms. Okay, so if we're going to parallel this one again, so the R total is equal to R1, R2 divided by R1 plus R2. So R1 times R2, that is equal to 10 times 5 divided by 10 plus 5. Okay, so that is equal to 50 divided by 15. So if we're going to use our calculator, 50 divided by 15 equals 3.33. 3.33 ohms. So as what we can observe here, the more the resistors we connect in parallel, the lower the value. Okay? So take note of that. So that is why the answer for this particular problem, the total resistance in a parallel circuit will be decreasing. All decreases. Next. So this will be the last problem for this particular video. And then we will have the last video for this review tutorial. Okay, so to complete the 6 series review in preparation for your written assessment. So now, let's try to have this last problem here. When a 1.5K resistor and a 100 ohm resistor are connected in parallel, the total resistance is, so the total resistance, basically simple. So we just have to solve this one. The R total, based from the formula that we discussed a while ago, R1, R2, divided by R1 plus R2. So that is equal to 1.5K times 100 divided by 1.5K plus 100. So to avoid confusion between the K here, it would be better if you're going to convert this one into ohms, not kilo ohms. So we have 1,500 times 100 divided by 1,500 plus 100. So maybe we can simplify this one. 1 times 0, 0, and then we have to add two zeros here from the 100. And then 1,500 plus 100, that is equal to 1,600. So that is equal to 150,000, okay, divided by 1,600 equals, so the answer is 93.75 ohms. This is the answer. Okay, so if you have some questions or clarifications, please comment down below and I will try to answer your questions as soon as I can. So good luck and see you.